Alright guys, second set of notes here for nuclear energy. So beta particle emission, we stopped there on the last one. So here's just an visual example of what's going on with beta particles, right? You've got that neutron that's breaking apart, and what happens is it creates a proton and an electron. So down here you can see where you've got that proton breaking apart, you end up getting an extra neutron, the electron gets shot out of there, and so it jumps up. You end up with two protons instead of two neutrons, and there we go. So it becomes stable. All right, so that's just an example of beta emission. All right, the other types of emission we get, we've also got positron emission. So this is where a proton kicks out a positive charge, which they call a positron, right? And there's a symbol that will be plus to become a neutron. And so the positron collides with an electron, annihilating both and generating energy. All right, so here's just a visual example, right? I've got fluorine. So as it goes through the process, right, that proton kicks out a positron and an electron. It becomes a neutron there, and so you see that the atomic number drops down by 1. So it goes from being fluorine to oxygen. So that's a positron emission. All right. You also get electron capture. This is where the electron, maybe from one of the inner shells, gets sucked into the nucleus, so it's close enough to get pulled in, and then combines with a proton and produces a neutron. So it grabs an electron from outside of the nucleus, and then when that electron comes in, it and a proton bond to make a neutron. So the atomic number is going to go up by 1, but I'm sorry, the atomic mass number is going to go up by 1. All right, and then gamma emission. All right, so here you get that energy or photon that's released from an unstable nucleus. So nothing really changes in that the atomic number and the mass number stay the same. Only big difference is now it becomes a little more stable, and some of that gamma radiation is released. Okay, and so those are our 5 types of radiation or radioactive decay that we see. Alright, so here's the question. How does an atomic number change when the nucleus loses an alpha particle, right? So if we're looking at that, it's going to lose a helium, so it loses 2 numbers for the atomic number, right? It's going to go down by 2 because helium's atomic number is 2. Beta particle, it's going to actually go up, right? That beta particle is going to get emitted, and the atomic number is going to go up. Gamma ray, nothing's going to happen. So then what happens to the mass number? Alright, so then on the mass number for an atomic particle, right, it's going to go down by 4 because the helium is losing 2 protons and 2 neutrons. And then on a beta particle, it's going to stay the same. It's not going to change, right? And then on a gamma, again, nothing's going to change, just that energy gets released. Alright, so how can we predict what type of radioactive decay will occur? Well, they're held together usually by really strong attractive forces. We call that the strong nuclear force. So electrons and protons, they're arranged in their shells, so they don't like to get rid of them. If they do, it's usually because they have odd numbers. Here, even numbers of protons and neutrons are usually the most stable. So if they don't have a balance there, they're more likely to give off some of that radiation. Right? So if it's got a 1-to-1 neutron to proton ratio, then it's generally very stable. Now the key rule here is when you look at the atomic number, the periodic table, right? Anything that's greater than 83 on the periodic table is usually not very stable, which means that it's usually radioactive. And you'll also notice when you look at the periodic table that that's where all of our man-made elements come into play, right? All the ones that are white on our periodic table. And so we're going to talk about how we get to those in the next slide here. So how do we get to those man-made elements or some of those elements that are maybe used for fuel? Right, we've got 2 different methods. We've got transmutation, right, and then nuclear bombardment. All right, so what's happening? So in transmutation, changing one element to another by shooting a nuclear particle at its nucleus. Right, so usually what's happening is you take all transuranium elements, which are more than 92 protons. Like I said, those are usually created synthetically in particle accelerators. So that's where we get all those man-made ones that are above 92. Okay, so how does the process go? Well, what they'll do is they'll take, say, for example, here we've got nitrogen, right, very stable. They'll then shoot a helium atom at it at very high speeds, right? So this takes very big machines, usually lots and lots of energy. They'll shoot it in there, and what will happen is that helium will collide with the nucleus of that nitrogen, and you end up with oxygen being formed, right? So it's gone up in atomic number, and then you'll get a hydrogen gas that'll split off, right? And so here's just showing you how the different things work. Nitrogen, there's my alpha particle, right, which is the helium, and then what I get released is a beta particle, a hydrogen, and I end up with oxygen. Okay. So here, if you're looking at the atomic masses, here's what's happening, right? You got lithium, it gets shot with a hydrogen. You'll notice that nothing is created, nothing is destroyed, right? I end up with a helium with the mass number 3, and then I end up with a helium with a mass number 4. So together, they're both the same, right? I end up with 7 and 7, and that's pretty close. And anything that's not quite comparable is just due to the equipment not being sensitive enough to pick everything up. Alright, so what are some applications of understanding and being able to use this nuclear bombardment and knowing how different things break down? Well, medicine purposes, right, it allows us to use chemotherapy, so we can kind of target it, certain things like cancer and other things that we want to get rid of. Alright, we also can use a nuclear fuel to power pacemakers, so that way the person doesn't always have to worry about the batteries running out or having to have a little plug hanging out of their chest where they have to charge. And then also one of the bigger ones is diagnostic tracers, right? You take some sort of chemical that it has a very short half-life, so it won't be too dangerous to the body. You inject that, it targets a certain thing, say be it like the thyroid or the pituitary or something like that, and then we can scan it and we can see what that organ looks like on the inside without having to open up a person or anything like that. Agricultural, and you probably just didn't realize it because you do it all the time. A lot of the food that you eat, especially canned goods, has been irradiated. Now, it's nothing really dangerous. All it is it's enough to kill any kind of bacteria or germs or anything like that that would be in that canned good that maybe didn't make it or didn't get killed by the boiling process of the foods being cooked. And then, of course, pesticide, right? Some of these particles that are nuclear material will cause bugs to where they can't breathe, and will eventually kill those bugs. Of course, this is a big thing. You got to watch out for getting into the water and killing fish and that sort of stuff. So, but it is useful for better crops. And then, of course, for energy, right? You got fission and fusion. And we're going to talk more about that later. But we use fission mostly for our energy process. But if eventually we could get to making fusion, right, creating our own little suns, then it would definitely be a lot easier than fission, and we would have probably an unlimited source of energy. Alright, so here's just a few pictures of some applications like an x-ray examination, right? So if you've ever gone through the airport or any kind of luggage handling, you see here they're using that to scan the bags. They also now have it to where they can do full body scans, and you look at if anybody's holding something under their clothes or that kind of thing. Here you've got some gamma ray analysis for, say, this is a catheter here for heart. They're just checking to make sure there's no flaws, which they're able to detect if the gamma rays would show up. Here's what we were talking about where they put in the dyes, right? So this would be a person's thyroid, and using that radioactive iodine, they can look at the person's thyroid and see whether it's got healthy or maybe parts of it that aren't healthy by looking at that scan. Here's an image of somebody's lungs using a gamma ray scan, and so you can see they're looking to see if they have healthy, or in this case it looks like they've got something that maybe they've got an infection or something going wrong with their lungs there. And then, of course, here's a cancer patient receiving some therapy. They'll shoot it through there at a certain specific area, so that way they're not affecting the whole body. All right. And so then, how do we detect nuclear radiation? Well, one of the ways that we do that is with a Geiger counter. And the way it works, it's pretty straightforward, right? You've got this electrode here, and this electrode has got power running through it, and there's gas around it, which is inert, and there's this little window, and whenever any kind of radiation passes through here, it causes the current that's between this electric rod and the outer wall to be disturbed, and when that gets disturbed, it causes a break in the power, which then causes the buzzer to sound and for the little meter to rise up and down, just showing that the electricity is being disturbed. This is the same process that actually works in your smoke detector at home, right? And so it's the same process. But that's it for the second section of notes, and so we will hit it up on the next section and talk more about fusion and fission.